So this is being recorded and we'll post it on our archive link on our website.
We already did that when you were very tired.
Don't worry, we'll turn the video down.
Okay, first, can everybody hear me okay? I kind of have some mic on. Eddie says that sometimes it's a little loud, sometimes it's not, so is everybody okay with the volume here?
No, I
Can't hear
don't
you.
hear you. I can't hear you.
We can't hear
Turn it up.
Okay, so I'm going to have to yell. I imagine this will work.
Great, it's probably gonna be really loud.
Yeah, can you hear me now? Okay?
Hello?
Turn something up.
Turn it up. Hey, we've got the link meeting working. I'm thrilled. That's one problem we don't have.
All right, how about now? You guys okay? We're okay. One more time?
Better.
Okay.
Oh.
All right, I'm going to try the handheld mic. And, yeah, I think that helps out a bit.
Mr. Microphone.
It's just like I'm ready to do karaoke now. Of course, you don't want me to. Trust me on that one. Today I'm going to do a presentation on indexing strategies. I did a similar one a few years ago before SQL Server 2014 came out. And this is basically a revamped version. Plus, I also incorporate a lot of feedback I But it's really important on a day-to-day basis. It's more about the strategy about how you develop indexes on your tables, from end to end, early in the development cycle, throughout the, the life of the application, what's really important. So in this presentation here, I wanted to try to, address some of that. And, the main thing is to keep the main thing the main thing. And a lot of times it's really easy to get caught up in the details, especially when you're a DBA, you're dealing with a lot of low-level stuff sometimes. But really think about, the problem space more from the business perspective. Oop. I don't know why it's only going one direction there. Okay, there we go. Sorry, there's a little bit of lag sometimes. So today I'm going to discuss, why indexing is important, when you should address indexing, which is, say, not just in production, but before you go live, cover some of the main concepts behind indexing, discuss some of the various design considerations, and there are quite a bit of them, and there's not a one-size-fits-all answer. Like everything SQL Server, I'm sure you've heard the pat answer, it depends, because it does. Every system's a little bit different, has a different workload profile, different sort of applications, et cetera. It's a general purpose database engine, so it has a lot of flexibility. But at the same time, that adds complexity to, what matters and what doesn't. And also I'm going to cover a lot of the, issues related to query and, and index tuning in terms of making them, efficient. When you talk to your boss and his boss or her boss, as the case may be, there's reasons why, you need to make the argument that you need to be able to spend time, with proper index and query tuning. There's real hard dollars associated with that. When your system isn't performing up to par, it's going to require more hardware resources. It's going to require more SQL Server licensing, which, as you probably know nowadays, is very expensive on a core basis, especially when you're dealing with like Enterprise Edition. The end user experience and, their productivity, it's just not going to be as good if they're sitting there looking at hourglasses half of the time and, that kind of thing. And, so there are some real business reasons for, addressing indexing. And of course, most of us, I guess, are DBAs here, right? Do we have developers in here too? Yeah, I see some nods here. So you got a little bit of a mix, which is typical for this user group. There's different audiences where, we'll address indexing at different points in their life cycle. From a DBA perspective, this is basically, I'm talking about the operational DBA, managing production mainly. Indexing will help improve the availability of the system, because when you don't have adequate index, you have to touch more data than is actually needed for a query, and that oftentimes leads to locking and blocking and deadlocking as well. So a lot of times, people say, well, I see some deadlocks, how should I address the problem? And they'll look at, hey, you access tables in the right order, things like that. That's definitely part of it, but a lot of times that's just a side effect of touching a lot more data than you should have to begin with in a given query. Indexing helps avoid that. Similarly, I'm sure you've probably seen performance problems like, that query from hell that uses every CPU in the system and, takes forever to run. Queries that just take absolutely forever to the point where they don't even complete. Those are all symptoms of just not having the right indexes. I'm sure you've also seen some, heavy TempDB usage, either sorts, hash spills, those kind of things, simply because the SQL Server just has to do a lot more work to, access the data when it doesn't have the right indexing in place. And I don't want to say that indexing is everything, because it's not. There's a lot to be said for the application design. The fastest query you can ever do is the one that you don't do. So if you have caching, think about things like, your state table, your lookup table, or the drop-down, box that's populated by the application. That doesn't need to be reloaded from a database query every time somebody, visits the website and, pulls the drop-down list. Just some smart caching, things that don't change or rarely change, can really help reduce the workload on the database server, indexing or not. Similarly, for things that do change, you can still do things like query notifications or SQL dependency, which is an application layer thing you can do to listen for changes to data. So you can run a query, subscribe to any change notifications, so that if the result set changes for any reason, you can rerun that query, perhaps refreshing the cache. It doesn't mean that every application needs to do that. It's best done like in the middle tier data layer where, there's a lot of, for example, you might have 100 web servers, and just a few mid-tier type servers where a lot of those connections get aggregated. That's the perfect place where you do your caching and query notifications. And that would help, reduce the, essentially the workload on the database, which is, the more headroom you have on the database server, then the lower your costs and the less you have to worry about indexing. Not to say you don't, but, you can't say enough for, once you have all the, right indexes in place, right, you've done everything right, you still have to have enough hardware for your workload. You can't skimp on not having enough memory to back up your database. I have clients that have been trying to run literally a terabyte database on 16 gigabytes of RAM. It just doesn't work very well. Not that it can't be done, but you're just not going to get adequate performance, if you don't have enough memory to, or any hardware resource to back up your workload. So, you got a lot of resources for, in terms of CPU, that's needed to back up, a lot, if you have thousands and thousands of, users, using, the application. There's just, that's the cost of doing business. I am a staunch advocate of being proactive, addressing things early as part of the system development life cycle, not reactively, after it's gone live in production. I know it's easier said than done. Everybody's got deadlines. You got project deadlines. It's not an easy task to do, especially nowadays when, like an agile development methodology is fairly popular. I'm a staunch advocate of, agile, by the way. but you have to have stories in there to be able to address, you know, the performance aspects of the application. There's a tagline, you know, performance is a feature, you know, not something that's, you know, to be thought of, you know, after the fact. Actively try to, you know, develop the mentality of developing for performance or with performance in mind while you're developing the application, not afterwards. You know, and a lot of it just starts with good common, you know, normalization techniques. You know, a data model where, you know, you have, you know, normalized tables with atomic data, you know, relationships with foreign keys. Every table has a primary key. A little asterisk by that because, you know, I don't think every table has to have a primary key, to tell you the truth. There's cases where you don't, like a log table, an audit table, history table, those kind of, you know, outliers. But the core normalized structures, you know, the entities in the database should definitely have, you know, primary keys and the associated foreign keys that goes along with them. You know, throwing, you know, unique constraints to get, you know, guaranteed data integrity, which of course you should have. I mean, everything's about the data. You want to protect the integrity of it because if you get garbage into the system, it's going to stay there forever until somebody, you know, either manually cleans it up or, you know, the system just dies. So, you know, just do those kind of things. And the beauty about that is you'll automatically get some fairly good performance out of the box because SQL Server is a relational database engine. So it's designed around a relational model, and hence the need for the normalized data model to begin with, because that lays the foundation to indexing. You know, you can't index stuff if, you know, for example, if you've combined last and first name in a column, instead of having first name and last name in discrete column, you know, it's going to be very hard to develop an index on that structure to do a last name search, for example. A lot of it is what I call common sense indexing. You know, and after you've already designed your, you know, your normalized database and you have your constraints in place, then think about what kind of queries the application is going to do. And those are, in the agile environment, they're basically driven by user stories. You know, I as a user want to be able to, you know, find, you know, people by their state and zip code, you know, those kind of things. Well, those are, you know, generally indexes that aren't really part of the data model itself, but rather things that you build on top of the data model. So, for example, there I would have, you know, on the address table, for example, I probably would need an index on zip code or postal code, I should say. You know, those kind of things. And you know, since you already have some free indexes you've gotten because of your primary key and unique constraints, you know, there's not going to be hopefully not a whole lot that you'll need to add on top of that. You know, that being said, I mean, I work with a reporting application where the users are allowed to basically sort and filter on anything. I mean, how do you index for that? You obviously don't want to put an index on every single column. Well, the key is just to, again, going back to the common sense things, what are the users most likely to, you know, search on? And you know, just concentrate on the low-hanging fruit. You know, look at the applications or the pieces of data that, you know, the users really are most likely to use. And then, you know, on top of that, you know, if your experience proves, you know, otherwise, is when the thing goes live in production, you can always add indexes later. But it's a lot cheaper to add indexing earlier than it is later, because then you don't have to go through that whole change management process again, development, testing, and all that goes along with it. You know, a lot of times it's a good idea, and you know, to add, you know, indexes on your foreign key constraint columns, although it's not required. I mean, SQL Server doesn't care. It'll be perfectly happy not having those. But that being said, it's not always, you know, appropriate. It's going to depend on the queries. If you have queries that, you know, you never delete data from your domain table, like let's say it's a status column, for example, you know, where you have, you know, pending and completed orders, those kind of things, you may not need to have an index on that table. Unless, of course, you're also searching orders by status and things like that. So, but if status is nothing more than, for lack of a better word, a lookup, then, you know, maybe, you know, you don't need to carry that baggage around of that extra index along the way. And there's also the, you know, there's going to be specialized queries. You know, you have that one query that, you know, people just hammer all the time. I mean, you know, that problem query. And that's where, you know, it's nice to have in your back pocket, you know, covering indexes and filtered indexes as well. And I'll I'll talk about that a little bit later, but in more detail. But there's I wouldn't go out of my way to make everything a covering index, because there's a lot of baggage that goes along with that too. You have to carry around extra columns that aren't part of the index key. The big problem ones are the tables that are going to be big, and as you probably know, that it's the ones that give you a lot of heartburn. You know, your billion row table, you know, or multi-billion row, as the case may be. I mean, those things are just plain a pain in the butt. So when you expect a table to grow large, think about it early. You know, is that a good candidate for table partitioning? You know, or perhaps you know, partition view if you're not running Enterprise Edition. You know, think about that stuff early so that you don't have to revisit it later when it's a lot more work to fix. You know, address that in the design phase. You know, you also have in your back pocket things like index views, which are great for aggregations, where it can pre-aggregate the data for you as long as you can live within the many restrictions of those. I'm not going to cover that kind of stuff in detail today, but, you know, just be aware that, you know, those are tools that are in your back pocket to, you know, address performance via indexing. One of my pet peeves is when you can see these data models all over the place, and for some reason they tend to perform fairly poorly. When every column has a column named ID and it is an identity column. Now, it's not to say that it's all bad, because every table should have a primary key, but that's a mindless, just knee-jerk, let's just put an identity column in every single table. In a relational database, data is related. So if you just use an identity as, for lack of a better word, a pointer to another, you know, table, then what ends up happening is that you have to do extra lookups. And I'll demonstrate this a little bit later on in the demo, but just keep in mind that, you know, identities aren't bad. I like them because they're incremental and they can make a pretty good primary key, but just don't do it mindlessly. Do your indexing with thought, you know, as you do that. And similarly, when it comes to the one and only clustered index that you're allowed to have on a table, think about which index should be the clustered index. It doesn't always have to be the primary key. There could be better candidates depending on how the data is actually queried. And of course, you know, we also have vendor applications, things that you can't really control, or maybe you work in an environment where, you know, development and DBAs are fairly segregated and aren't allowed to talk to each other for some reason. You know, if that's the case, then, you know, you can still add indexes after the fact, because, you know, you have, the nice thing about being a DBA is you have access to the DMVs, where it can show you the actual queries that are being run, which ones are the most expensive, what indexes are being used, as well as which are not. You can see the query plans. You have a lot of tools at your disposal to be able to really understand better, you know, the impact that indexing or lack thereof has on the system and workload. How many of you use a third-party tool, you know, like Quest or Spotlight or something like that? I got a few. I actually expected more. It kind of depends on the environment. They're not cheap a lot of times. I mean, you know, you've got to pay to play. But in lieu of those, you can, you know, you can, out of the box, you get, you know, management data warehouse with SQL Server, or you can just build your own custom tool set to essentially grab data from, essentially these tools operate similarly. They grab data from the DMVs, sometimes also with extended event or, you know, SQL traces. They pump it into some data store, and then they run reports on it in mine. And, you know, you just facilitate that with some alerting when things are high CPU for long periods of time, those sorts of things. It's all about monitoring and things. But there is a gold mine of data that SQL Server just has out of the box in the DMV. So don't throw that away. I mean, definitely, you know, you can use it in, you know, with relatively minimal development, you know, track that stuff over time. So you can see how the workload changes over time, so you can, you know, be better as far as proactively managing it. I always like to, a lot of times people think about disk when they think about indexes, because, you know, it's just that at least I do, because that's the way I grew up, if you will. It was always, you know, I/O is always the slowest media on the computer, and it takes forever to get data from disk so that you can work on it. Well, in reality, you know, SQL Server only operates on data in memory. It never operates on data on disk directly, you know, when it comes to doing queries, updates, deletes, all of that. It first has to bring it into memory from disk, you know, if it's a persisted table. But once it's there, it'll stay in memory forever until, you know, you shut down the system, or if that space is needed for something else. But the whole key is that it has to be in memory to be used. So logically there's a hierarchy of storage, everything from the processor cache, you know, through the buffer cache, you know, the buffer pool extensions, the storage system itself. It's got cache, you know, built into it. And then finally, there's some place where that data gets stored if it is a persisted table. Now, with SQL, you know, 2014, with memory optimized structures, you have the option for it to be non-durable, therefore it never gets written to disk. But barring that, you know, all the data eventually is going to end up on media. But it's not really operated on that storage. It's actually operated on in memory. So the key is getting the data into memory, you know, efficiently. That's the only time disk is really touched. So the purpose of indexing, think about it, at least I suggest you think about it, more about how to efficiently access data in memory. And if the data just happens to be in memory already, then you're good to go. If it's on disk, then, you know, you don't really have direct control over that anyway. That data is going to be in memory if it's frequently used, and if it's not, SQL Server just uses a least recently used algorithm to you know, purge data from memory and bring in more active data as needed. So don't think about SQL Server as really reading and writing from disk. Think about it using data in memory. And of course, that's true, especially if you're dealing with memory optimized tables, which by definition have to be in memory. A lot of times I hear DBAs be excessively concerned with fragmentation. And I say excessively because, you know, when there's a performance problem, knee-jerk, reorg the table, problem goes away, problem solved. Well, a lot of times it wasn't the act of defragmenting the index that fixed it. It was the side effect of the stats getting updated, or the side effect of the plans getting purged from cache and a new plan generated. So if you better understand the problems that is actually happening at the time, then, you know, I think you're better off, rather than just saying a reorg isn't to fix every problem. What I'm trying to say, you're doomed to repeat it over and over again. Even though, not to say that you shouldn't reorg tables, don't get me wrong, you know, or at least you know, rebuild them for that matter. But you know, the reason that you know, fragmentation, you know, affects or is a problem area in general, is because it wastes space in memory and it wastes space on disk. And there's different types of fragmentation. The first type is internal fragmentation, and that's simply unused space. You know, every page, you know, has both used and unused space inside of it, unless it's exactly 100% full, which is fairly rare. But that unused space essentially is internal fragmentation. And it's not all bad in the sense that when there's unused space, that means from an indexing perspective, it has a place to insert new data or expand existing data. And that will therefore avoid page splits. So that's about the only thing good about internal fragmentation. The downside is that it's going to use more memory, it's going to use more disk space, you're going to need more I/O for the same amount of data. Also, you know, it's going to reduce your page life expectancy and all that. It's just, you know, it's just not generally a good thing. However, you know, if you just reorg on a regular basis, that will help, you know, reduce the fragmentation. In other words, make the pages fuller from an internal fragmentation perspective. As well, you know, and also, you know, it depends on your fill factor, which fill factor, by the way, you know, determines how full the index leaf nodes are when you rebuild the index. So by having a high fill factor, you're making them fuller, and therefore, you know, they're more dense. So you can fit more data in the same amount of space in memory and on disk. External fragmentation is a different concept, even though it's also called fragmentation. It basically just means that the physical order pages are different than the logical order, or the data. The downside with the pages being out of order is that if I'm doing an ordered scan, and think about spinning disk here, spinning media, then every time the head moves, that's a physical operation. And because it's physical, only that takes a long time compared to an in-memory or an electronic operation. And it really can make a really, really big difference if you have a really large table that's, fragmented in terms of external fragmentation, and it's on spinning media. You take that exact same table with the exact same fragmentation, put it on solid state storage, and there won't be any performance hit at all, relatively speaking. So there's definitely, some benefit to, so you have to think about the hardware aspects of your system as well sometimes, even though I hate to do that early in the development phase when you might not even know what your storage subsystem is going to look like. But the point being that, with the fragmentation, it can be mitigated by having solid state or, and I also mentioned up there, if you have dedicated files and file groups, then you won't have to deal as much with the, the fragmentation due to other objects getting in the way, if you will, of the other storage. So with a single file, your tables will be commingled, or a single file group, I should say, which isn't all bad, but it's it's just a consideration if when it comes to fragmentation. It's just the nature of the beast. And then there's physical fragmentation, which just means that the allocated space on disk the segments of the file itself are not contiguous. So, for example, if you have a fragmented hard drive and you create a big data file, it's going to be fragmented automatically because it's going to have to, spread that data across the disk in various chunks. And that fragmentation, has the same sort of effect as, the external fragmentation, where if you're doing a scan, the head's going to have to move to get to the data, and that could be less optimal than if it were, contiguous. But typically in SQL Server, we don't bother shutting down the database engine and running a Windows system defragment and that kind of stuff. Just don't do autogrows. That's at the end of the day, if you have a dedicated volume for SQL Server data files, pre-allocate the space you're needed, don't do autogrow except as a safety net, and you're pretty much done with that. And similarly, solid state can mitigate that. So with traditional B-tree indexes, there's only a few options really that you have. One is whether or not the index is clustered or not, unique or not, and optionally you can add included columns, meaning those are columns that are not part of the index key, but they're additional columns that are kind of along for the ride. So that if you have a query that only needs the index keys and a few additional columns, it doesn't have to jump all the way to the data pages to get those additional data that's needed for the query. So therefore, it covers the index and without needing to actually access the data page itself. And that can be, as I mentioned earlier, fairly useful for specialized queries where you need to have high performance. Filtered indexes, which is really just a where clause on top of the index for non-clustered index, allows you to, as the name implies, just filter the index so it only contains those rows that satisfy that the filter predicate. That's really useful if you have, let's say, a query that typically only references a fraction of the entire table, and by filtering out those unneeded rows in the non-clustered index, it makes the non-clustered index very small, so it doesn't need to have as much memory, and it doesn't have to be maintained on the updates of all the other values that are being excluded. So there's definitely some benefits to be had there.
Dan?
Yes.
Question. When you have extremely large tables, how much of that index is tried to be put into memory? Besides, it depends on the query.
So the question was, and I'll try to regurgitate correctly, so if I have a very large table, how much of that index does it try to keep in memory? SQL Server he basically tries to keep data in memory in general on a least recently used basis. So the more often you use something, it'll stay in memory. So the most stuff is going to stay in memory if you've used it recently, until that space is needed for something else. However, indexes get a little bit of a bump in the priority, and that's why it's not just a regular least recently used algorithm. It's an LRUK, I think LRUK2 is the name of it, where it kind of gives indexes a little bit higher priority, so they're not aged out as fast as regular data pages, with the anticipation that indexes are more likely to be reused. Even they might not be that recently reused by the clock, they probably will be because of the nature of indexes in general. They're used to locate the data. So as far as how much of the index will be in memory at any one time with a very large table, it will be those index pages that were most recently used from that table. Of course, barring a memory optimized table where the index is only in memory and will always be in memory. Did I answer your question okay then, Julie? Okay. Any other questions while I'm talking about the B-tree stuff? So B-tree indexes are pretty good for if I need to retrieve a single row. It just traverses the B-tree from top to bottom. I'm not going over, by the way, I forgot to mention this earlier. I'm not going over a lot of the internals of the B-tree structures and all that. I know that Kathy Kellenberger did cover that at the last BI meeting, and I didn't want to be redundant for those folks that go there too. So I'm trying to address this at an intermediate level with the assumption you already know a little bit about B-tree indexes and that kind of stuff at least. So if you're brand new to SQL Server, my apologies for not covering that, but I really would rather concentrate more on the strategy behind the indexes and the operation. But at the end of the day, they're still B-tree indexes are still pretty efficient for singleton lookups, as well as any sort of ordered processing that SQL Server might have. That might be, for example, if I'm doing a range scan or a seek followed by, the scan of the matching rows, or things like, I'm sure you've probably seen them in your query plans, merge joins, things that require ordering to actually work. Because in order to match or do a merge, the data sets have to be ordered. It's pretty efficient regardless of whether or not the data is, in memory and on disk, but it is a compromise nonetheless, because unlike memory optimized index, traditional B-tree indexes, that data might be on disk, so it can't have to, it doesn't have the same literary license that a memory optimized, B-tree does. Which, and this is, and so basically, memory optimized B-tree indexes are similar, but like all memory optimized indexes, they never, ever are on disk. A memory optimized table that data will be on disk, at least, the committed version of it. Because what SQL Server does is it will rebuild all of the memory optimized indexes from scratch when that actual data gets brought into storage, where it gets streamed into storage, for access. So essentially it's building all the indexes up front and then maintaining them in memory and then throwing them away when you shut down the database engine. So obviously that's a little bit expensive, but at the same time it runs like a bat out of hell once it's running. The nice thing about the memory optimized B-tree structures is that they're literally memory pointers. So rather than having a doubly linked list of forward and back pointers that are needed to access or to maintain the index, levels on disk, there's a lot more flexibility because the cost of going from one place to another in memory via pointer is like sub-nanosecond. It's just very, very fast. So it's, it's nothing to, it's not that big of a concern. So, the memory, the B-tree indexes in I call them B-tree, I should have said BW tree, which is just a similar in concept, but, a different implementation of the memory optimized indexes, where you still have, the concept of a hierarchy. There are just some minor differences, like, trying to think of a good example. like the, for example, in the B-tree index, normal B-tree index, I believe it's be getting this backwards, but like every index level points to like it has, the upper index levels have like the highest key of the next lower index level. Whereas on a BW tree, it's the opposite. It has the lowest key of the next lower level. Just little things that really don't matter much from a conceptual perspective, but they are differences nonetheless. There are restrictions, such as there's only such thing as a non-clustered B-tree index, because it makes no sense to, or I shouldn't say no sense, but it doesn't have the same benefit as an on-disk index would. So these are all non-clustered indexes. Also, you can only have non-unique, B-tree indexes, except for the primary key. The primary key of a memory-optimized table still can, be a unique index. You can't have any included columns, and you can't have any filters. Now, I can see the no need for the included columns piece because everything's in memory, including the table itself. It's so fast to get to it. Why bother to replicate the same data in memory? Because that's what it would be doing. But as far as the filter, I'm not exactly sure why they have that restriction, but I'm sure there's a good reason for it. And it's really the same sort of benefits the BW tree index has the regular B tree index for disk-based or tables that are that could spill the disk. The has pretty faster singleton equality lookup. Not quite as fast as the hash indexes I'll mention in a minute, but it does provide the ordered retrieval that you need for like merge operations and partial index key lookups. It's not, as I mentioned earlier, these indexes are not stored on disk, so they're always rebuilt. Now, one of the best things about in-memory or memory-optimized indexes is the hash index, where you can't get any faster in terms of singleton lookups because it doesn't have a B-tree structure at all. It just has a hash structure that points to the address in memory of the data page. And, so it's very, very fast, and, just like any sort of hash in-memory lookup. But, of course, there are some restrictions to it. They're listed there. One difference, though, is because you can only do really singleton lookups with a hash index, the order of the key columns don't matter, but they do for regular indexes, as I'll mention in a few minutes here. You have to specify a bucket count, which is the estimated number of unique values of that index you expect, just so that it can optimize its memory structures. There's more cost if you have more collisions of a hash index, and by doing this, you're optimizing the in-memory structures. They're really fast. That's all I can say is really, that's a big thing there. You can't use them for ordered retrieval. That's probably the biggest differentiators there. So changing gears a little bit, the concept of incremental keys simply means that a key that increases with every value that you insert. So usually you use an identity or a sequence or a date time or a new sequential ID, something like that, to assign those values. The advantage is that it reduces fragmentation because you're always adding data to the end of the index. It also improves the page life expectancy and the locality of reference, meaning that it's likely that once you insert data, you're probably going to use it again pretty shortly. So, it's generally the most recent data is going to stay there. It reduces I/O for inserts because you're inserting data into the same page all the time. So that one page is going to have many of the recently used or added data, in contrast with a random index or one that has random values assigned. Now the downside to an incremental value, and you generally only see this at the extreme high end, but if you're inserting like tens of thousands of rows a second for multiple threads, then you'll actually see some page latch contention, simply meaning that the access to the data in memory has to be serialized while SQL Server is updating that page. And in that case, especially if your storage subsystem is slow, where you end up dirting all the pages in memory, it can really cause a lot of latch contention. So that would be a case if you back it up with a like solid state storage, that a random key would actually perform better for literally tens of thousands of concurrent inserts a second. Also, one downside to the the incremental key is just the ascending key problem, where since SQL Server keeps statistics of the index, it doesn't know about the most recently inserted ones. So it's assuming that there are no rows beyond the highest value it last knew about. So it can incorrectly estimate the number of rows that would be returned by a query. Generally speaking, it's going to depend on your queries. I personally haven't run into the problem where that has caused an issue for me, but I have heard of cases where it does, especially with more complex queries where they're really sensitive to those row count estimates. Now, random keys, as the name kind of applies, I really just mean non-incremental. This could be anything from, let's say, an account number that comes in from an external system to a GUID or a new ID value, essentially where it's not incremental. So the advantage of that is that, in contrast to what I mentioned a minute ago, it avoids the page idle latch contention. You don't end up with that hot spot at the end of the table. The inserts are distributed roughly evenly throughout the table. And it avoids that ascending key issue I mentioned. The downside, though, and it's a biggie, is that it increases I/O, especially when you got really big tables. I mean, by that I mean to say increases I/O by an order of magnitude. So if you're doing a lot of inserts, for example, and randomly distribute, let's say you have especially when you have a clustered index on that, it's really going to be slow. I mean, by orders of magnitude slower. So it's definitely a big consideration. And of course, if you're assigning the data, matter of fact, this question actually came up in the news group just yesterday. The guy had a new ID on his clustered index and wondered why it was running so slow after he started loading his table.
Ouch.
And I said, hey, just make it a new sequential ID and you're done with it. It's really a simple fix. Not that of course, some other folks recommended an identity column too, which is another way to address the same problem, but So some of this is, I'm sure you probably already kind of heard, and that's when you're designing your indexes, mind you, this is after you've done your data model, your common sense indexing and all that kind of stuff, you really got to know what those queries are going to look like. Or if you're doing reactive mode indexing, it's really the columns that are in your join or where clauses. There's no reason to create, the keys of the index that are on something besides your join and where clauses at the end of the day. Now, a lot of folks they like a lot of single column indexes instead of multi-column indexes. Not to say that's always right or that's always wrong. It's something, again, it depends, kind of thing. But if you have more than one column in the same table that's being referenced in your join and where clauses, and an equality predicate, that's a candidate for, a multi-column, composite index. If ever you end up with an index that you've designed for performance reasons and it ends up it's unique, declare it as unique. It does help the optimizer better estimate the cardinality on the queries. And I've seen that influence the execution plans fairly significantly just by throwing the word unique on the index. Or, of course, you could alternatively make it a unique constraint, too. It's important that, the idea is as I mentioned earlier, is to touch only the data that you need. And as long as the data that you're asking for matches the leftmost columns of the index key, that's exactly where you're going to touch. No more than the data you need. So, I suggest being generally conservative on adding, non-clustered indexes and included columns, all that kind of stuff. In other words, just justify them. Just think about, hey, is this really justified to create yet another index on this table? I mean, you can't, you can go overboard, but at the same time, is there a downside? The downside is, in the last bullet there, too many indexes, you got more storage, more maintenance in those indexes, because every time you insert, a row or update the keys, that's going to change things. There's compile time, hit, because SQL Server considers a lot more, when it comes to, when you have a lot of indexes on the table. And also it increases the likelihood of SQL Server doing something dumb. It has too many choices. It fails due to a, good enough, what it considers to be a good enough plan. And lo and behold, you end up with a bad plan overall.
Dan?
Yeah.
Kathy had mentioned that at her lecture that she actually saw when a table had a lot of indexes that the optimizer got to a point and just threw up its hand. It didn't analyze all of them. It just was like overwhelmed with
right.
options. So I don't know, where's that happy medium of how many indexes are too many to where SQL will throw up its hand and just forget it.
So the question is, how many angels can fit on the head of a pin? No, it was at some point the optimizer is going to do that, good enough plan found thing and not analyze all the, indexes and the permutations thereof. What is the right number? I really don't have an answer. It's going to depend not just on the number of indexes on that table, but the overall complexity of the query. That's where it gets really nasty. Case in point, I deal with some pretty nasty large tables that also happen to be member tables of a partitioned view. So what that means to SQL Server is that I'm going to have a union all view of dozens and dozens of tables, each of which could theoretically be partitioned or indexed differently, and then that view gets joined to a bunch of other partition views, et cetera, and it can get really nasty really fast. The real solution to that problem is table partitioning, where you basically you're guaranteed to have the same indexing on each of the partitions. But the downside is that for our product we can't require Enterprise Edition. We have to let customers be able to run standard. So we're kind of caught between a rock and a hard place. I can't use the right tool for the job. But I'm sorry I don't have an answer for your question about what the optimal number is. It's going to be, when you see the point where you've added indexes for good reasons, then it might be time to pick and choose which ones you need to throw away, so you don't end up with the problem query, or perhaps throw index hints on it or plan guides in order to address the anomalies. So the order does matter as far as the key order. The most important thing is to specify the quality keys first. So, a lot of times you might have, a situation where you're looking for all the orders for, a given date range or for a given customer as well. So you say where customer ID is equal to such and such, and, the date is between the first of the year and the end of, the month or something like that. Although you might be tempted to put the date first because that's part of the criteria, the downside that might be more selective than your customer ID. Your date your timestamp. But don't put the most selective column first unless it's used as an equality predicate. That's kind of the point I'm trying to make there. There are exceptions to that general rule about equality predicates as well. And that's when you have a one-to-many join on a related key. And I mentioned earlier about having that anti-pattern of identity on every table, rather than perhaps having a composite key. Unfortunately, I'm going to be running short on time, so I don't know how far I'll be able to get into my demos. But in the AdventureWorks database, there's an order header, an order detail table. Something you see all the time in e-commerce. Well, what their design pattern is they have a identity column on the order header table, basically your order ID, or sales order ID, to be more exact, and they also have a related sales order ID that came from that, identity value from the header table in the detail table. So you have a one-to-many relationship. So to form the primary key, they also created a sales order detail ID as a identity column, but they didn't mindlessly just make that by itself the primary key. What they did is they made it a composite key of the sales order ID from the order header table and the identity column from the related sales order detail table. The beauty about that is now when I say, okay, give me all the order items for a given order, that's going to be the same order as the clustered index. And I'm going to basically touch one page, get dozens and dozens of line items from that order, and it's going to really perform well compared to had I just put an ID column, identity column on there and not done that. So, consider the, different design patterns there. And in some cases, you're going to end up with a, index that could be used by different queries. So, sometimes you need to refactor. You don't want to have like for example, one query uses column A and B, another query has columns A, B, and C as equality predicates. You can get away with one index of just A, B, and C. You don't have to have both because that one index will be useful to both of them. And I kind of mentioned this a minute ago, but that is pretty important. Then after your equality keys, then you specify the other criteria, which typically are going to be like, range keys. Let's see, so included columns I kind of spoke to earlier, so I don't know if I really need to go in any more detail there. Yeah, the nice thing about included columns, in the older versions of SQL before they introduced that feature, you actually had to add the columns to the key, which means you had to eat that maintenance of having to maintain the correct key order. Filtered indexes are really handy for, as I mentioned earlier, like things like a status column, like if you're only interested in things that are pending, but you don't care about the completed orders, those kind of things. It can really be beneficial because it reduces the physical storage on disk, and because there's less storage on disk, you could actually fit that, if you use it often enough, like Julie was mentioning earlier, you'll end up with the whole index in memory. So, because it's a lot narrower without having to, incur that I/O overhead. So, and of course it reduces overall cost because you're not maintaining that index for the values that have been excluded by that filter. All right, I'll see how far I can get on the demo thing here. Hopefully I can share my screen properly, so give me a second. I'm trying. Give me 1 second here. I'm kind of Skype challenged. I had to use the web version of this thing, and I have absolutely no idea how to navigate the darn thing. I might have to just forego this unless Eddie's around or something. Yeah, let me just move on then. My apologies there.
Eddie to come and help. You want to ask Eddie? Eddie can come in.
Yeah, if you could, maybe I'll have time to go back to it. I still have enough material that I can, Okay. But I'll keep speaking to this rather than...
Windows plus capital P.
Oh, I knew that. Yeah, like right. Windows plus capitals what?
P.
I knew that. Reminds me what I just remembered.
Oh, Windows and P, no plus sign. Windows P.
That'll just project,
Yeah, exactly. That just gives me the extend option. I just need to share another application.
Oh.
Because right now I only have PowerPoint for some reason. I just don't know how to do that on this thing.
Windows plus control and elbow.
No, I'm going to have to hit F1 or something here. You know?
Windows control
It says, or
spacebar.
drag it to the second window.
Oh, I think that is the key. Okay, drag it to the second window.
Yeah.
After holding down the Windows key and hitting on your
Oh,
head.
no.
Except the key.
Hey, Brian.
Oh.
Hey, it's snapback. I was almost there.
We believe you, it was there.
Maybe it's just shy. Maybe it's
Oh, it's to the right. That's my problem.
Hey.
Come on.
Let me see if I can figure out where I'm at here. It's a little bit awkward on this.
I can't imagine.
All right. Yeah, here I just did a little data mining, or just a query just to list the current primary key indexes that they had on AdventureWorks. You know, not that I like using AdventureWorks as like the end-all, be-all, best data model, because it's like, you know, a lot of it's good, but you know, it has its own issues. I've yet to seen the perfect data model, by the way. Has anybody ever seen the perfect data model in a database? Okay, because I mean, a lot of it's going to depend on your experience and your opinion. So you know, there's not one right answer, I don't think. Okay. Yeah, make sure I got it. This is just a list of all the single column indexes that they had in AdventureWorks. And as you can see, most of these are identities, but not all of them. The ones that are not are things like the were either assigned, they're one-to-one relationships between like business entity ID, where that's an identity column from another table, and they just migrated the value to the related table. But there are cases where they use the natural key as well, like for example, currency code. I mean, I assume that's the ISO currency code. I think culture ID is one. Anyway, there's cases where they don't. So the point I'm trying to make is just that, you know, identities are good, but they're not the perfect thing in all situations. Especially if you already have a natural key, you know, that fits your purpose. Now they also have a bunch of composite, you know, primary keys, where you know, this is one where I wanted to mention about the I mentioned earlier about that order detail. So fortunately, I have a minute, I think. Whoops. Kind of keyboard challenge here. Yeah, and they have a bunch of composite keys here. I think, yeah, these are just the primary keys that are composite ones. And most of these are clustered, as you might expect. I mean, it was the best choice, I guess, as the developer felt. The only exception, I think, is this one here. What is that? Oh, yeah, product photo, where I think that product photo ID is actually a hierarchy ID. So if I remember right, so they chose to make that one. I could be wrong about that. Maybe, yeah, I think that's a hierarchy ID. But anyway, you know, that's just how they chose to design their, you know, their database. But let's see. Yeah, and here's all the remaining indexes, you know, all the indexes on there, including the, you know, some of the primary key constraints that are, you know, some of these are clustered, some of them aren't primary keys, that is. Yeah, so here, the AK are the unique constraints, which are alternate keys in this case, you know, from a data model perspective. But anyway, the point being that, you know, that they do have quite a few, you know, indexes on this database, but you don't see a single table that has, like dozens of them, I guess is what I'm trying to say. Yeah, so I mean, you know, that's just a little data mine, just to get an idea for that model. Now here's the, I was kind of alluding to this earlier, I spoke to it a little bit, where, you know, to get all the orders for the customer, in this case, I specified the customer ID, you know, just in the sales order header, and, you know, and to get the details, it's just a simple join, you know, with the sales order ID. Because of that indexing strategy I mentioned earlier that they used here, where they, see here for 1 second, I got. Yeah, I just want to show the execution plan there. In this case here, because of the, you know, with the composite key on the sales order detail table, it's able to use the clustered index seek on both those tables fairly efficiently. Although, you know, this warning here, by the way, is just because they have a computed column that says will affect the cardinality estimate. Nothing to worry about in this case here, but this is a pretty good plan. So if this is a fairly frequently, you know, executed query from the you know, customer website, you know, the user, I would expect to get pretty good response time when they select their order details, you know, for a specific order. But when I was poking around the database, I did see some interesting things. Like, for example, on their they have a status column in their sales order header that they have they don't have a foreign key relationship because they don't have a related table, but they do have a check constraint that basically allows all values from 0 through 8. However, their extended property description only says that they had 6. You know, so basically it's like any real system. You're going to have development in progress, stuff gets promoted before it's ready, or abandoned development, whatever. But anyway, to mitigate that, I just went ahead and created a you know, a lookup table, if you will, or a domain table, inserted the actual valid values, and then went ahead and just created an index on that foreign key column. The only reason I created that index is because it's going to depend on the queries. Like the other query I just ran, where let's say the customer, rather than display that not so user-friendly number of a 5 for completed or a 1 for in progress, I like to see a real description, something that isn't necessarily assigned by the application code, you know. But in the in reality, though, they only had completed orders in their database. You know, this is the AdventureWorks sample database, by the way. So, you know, that doesn't really necessarily need it. But by creating that foreign key constraint, it really didn't benefit the query when I was looking up the orders for a specific customer, but it was beneficial for a different use case, like customer service, for example, where they may only be interested in back-ordered orders, or orders that are, you know, orders that are basically orders that are not completed. So what I did is I went ahead and created a filtered index on that that query. Well, I skipped ahead a little bit. Let me go ahead and just run some of this. Okay, so let me just get a query where I list just those orders that are, you know, needing approval that, you know, somebody in customer service might run. Forgot I didn't create my table here. I had restored the database just because I didn't want to wanted to start fresh, but I'm running a little behind, so I just want to get through this demo and then I'll finish up here. Right, so I replaced that check constraint with that, that lookup table.
Check and say.
Yeah, I think this is the same query again here. No, it's not. I'll just skip ahead a little bit. I was using my keypad instead of my mouse. I forgot I had the mouse hooked up to this thing. I'm kind of keypad challenged too. I'm so used to using keyboard shortcuts. I'm trying to do this one-handed. It's really tough. Yeah, I just want to try to get that execution plan of this one here. So here I'm selecting all the in-progress orders. Yeah, and I'm joining to that order status table. I looked up. Yeah, I see a key lookup there. So anyway, let's see. I thought I got a missing index warning when I last ran this thing. I don't see it here, so I don't know. I might have created that other filtered index already. I think I did. Yeah, my apologies. I tweaked this demo right before this presentation, and I think I didn't. Yeah. Anyway, it was a good filtered index demo. Darn it. Yeah, what I had done is the missing index warning actually did not recommend a filtered index. But since I was only interested in indexes that were for the, basically I don't care about the completed orders. Customer service doesn't deal with those guys for the most part, so that wasn't really important. But a relatively few number of orders in the database were completed, so I just said where the status is not equal to 5 and create an index on that one. And I got some good execution plans, and furthermore, it reduced the physical size of the index by a couple of megabytes. A couple of megabytes. I mean, it's not a big, nothing to write home about, but it can add up, and especially if this was a real-world example with a large table, that could be a big deal. So that's why I wanted to mention that one there. Now, let's see if I can actually get back to the PowerPoint. This is going to be really fun. Wow, it actually worked. All right. I just want to speak to a couple things because I'm running short. I'm running over, so I'll just get a couple things here. When it comes to soluble expressions, I think this is worth speaking to because this is something that will stop the indexes from getting used. It just means it's a searchable argument. So what it means is that you need to have the index basically alone on one side and your where and join clause predicates. The common gotchas that make them insoluble is applying a function to a column. You compare to a column that has a different data type, and the other data type has a higher precedence. So SQL Server has to convert the column to the higher precedence data type before it can do the comparison. And it can't use the index because it's catch-22. It doesn't know what the value is. It needs to search on until it does that. In leading wildcards and like expressions. So, just a couple examples. I see this all the time. Just saw it this week on the news groups or the forums, I should say. Years equal to something. Where you apply, instead of the order date. Now, if it's a date, just a regular date column, you can get away with just putting a between. If it's a date time column, you could do an exclusive begin date, exclusive end date, and that'll address an issue if you have a time that isn't midnight. But that allows the index to be used efficiently. Another common one I see is where you have a non-Unicode, like a varchar column, like a count number in this example, but you compare it to a Unicode parameter or a Unicode string. Well, Unicode has a higher precedence data type, and a lot of not entity framework, but a lot of ORM frameworks they like Unicode, so they like to make everything Unicode, And then what happens, you run the Java application with the ORM mapping using NHibernate or something, and it decides to put Unicode for everything, and none of the index gets used. And guess what? You got blocking, deadlocking, all that nastiness. There's not a real good solution to a leading wildcard if you really need to have that functionality. So really in SQL, the only thing you can do is, a full text search. Or just say, hey, do you really need to search the entire string for what you're looking for? And this is one I ran into just yesterday, or I'm sorry, not yesterday, but I think over the weekend, where somebody was using a file table, which are pretty cool, but the way on the where clause they say where path locator is equal to the .to string is equal to the file table ID, which is the primary key of a file table. Well, to string is basically a method, which is just like using a function. So it had the same net effect. So I just had them do a little refactoring there, and it suddenly it went down to 5 milliseconds. What a surprise. So it really can make a huge difference in performance and whether or not those indexes are used. But anyway, like I said, I'm running a little bit over, so I'll call it quits here. I was going to talk about stats and stuff too, but whoops, went a little too far. Let me see if I can. Yeah, just going to have a couple references on there. One last thing I want to speak to, I'll skip over statistics, but with SQL Server 2014, they introduced a new cardinality estimator, which really can affect how the indexes get used. So it's a different way of interpreting existing statistics. With the new estimator, it assumes that, let's see if I didn't, yeah, it assumes that there's some correlation between the data or between the columns if it's in the same table. Like, I don't know, your zip code in your state, for example, there's probably a little bit of a correlation there, whereas the old cardinality estimator didn't assume any correlation. It just went on raw mathematics and algebra to figure out, what the row count estimates were. And just at the end of the day, it can be 1 step forward and 1 step back, or 2 steps forward and 1 step back, or 1 forward and 2 back. It's going to depend on your workload. So just be aware that that behavior changed in 2014 for the cardinality estimation. If your database is in the 2014 compatibility level, then it'll use the new cardinality estimator. If you have problem queries, you can either turn on trace flags or change the database compatibility mode back to the 2012 or earlier version, and then it'll use the legacy cardinality estimator. But I've seen people have issues with it, and I've seen people have improvements with it. It's just going to be, hey, it depends on your specific queries. So anyway, I figured that was worth mentioning as well. Are there any questions before I wrap it up here? Yes, sir.
Do you have any thoughts on naming conventions for indexes?
Do I have any thoughts of naming conventions for indexes? Yes, I do. I tend to be more anal about the primary key and unique constraints, where I use the Hungarian notation for indexes as well. I put just IDX underscore table name underscore some uniqueifier. At places I've worked, we've used like at least the first column, if not others, as part of that uniqueifier, because the only requirement for an index name, in other words, one that's not a primary key or unique constraint, is it only has to be unique within the table. And I see that a lot of folks, they don't even bother to put the table name in there. That doesn't make them IDX 1, 2, 3, or CDX for the clustered index. Well, Microsoft does it. What can you say? Yeah, if you look at their system tables, that's exactly what they do. But my personal preference is to use the table name, for index naming conventions, followed by, a uniqueifier that might have some use, like being able to identify what at least the first column is. Obviously, if you got a big composite index, you don't want to list out all the columns unless you're really, you only have 128 characters. So.
Dan?
Yeah, Julie.
So where I am for naming convention, we have a 3-letter prefix. this is, we know that the indexes are our indexes, you know, X symbolizing index, and then I have the next addition is it unique, or is it clustering, or is it non-clustering? So it could be XN, and then the next one is uniqueness. So XNN is a index that is non-clustering, non-unique. Or you could make it XCU, or I don't know. I could look it up and get it for you. But it tells me right away, and then I do the table name and then the columns, you know, or something that's meaningful that represents the columns. But it tells me when you're looking at your execution plans, oh, it's using a unique index. And this is usually if I have it clustering on something that's besides the primary key. I deal with a package, so. But usually all the indexes that I'm adding are non-unique, non-clustering. So.
All right, yeah, just, I know I didn't get the mic over fast enough for Julie, but anyway, she has a naming convention where she embeds both the clustered and the uniqueness attribute is just a character like NC for non-unique clustered or whatever, and I've seen that used as well. And then also consider other attributes you might want to put in there, like the filtered or not, for example, you know, that kind of stuff. So, you know, it just depends on how anal you want to be about it and how much value you have for, you know, going through the effort of coming up with a good name. But I'm a staunch advocate of good naming conventions, by the way, so don't get me wrong if I don't care much about indexes, because I do. Yes, sir?
I find the naming conventions are invaluable when you're looking at execution plans. It's going to tell you what index looking at, and I have a package that I deal with as well, and I can tell right away, oh, it's using one of the vendor's indexes. Oh, I can tell exactly what column. No, wait a minute, no, I can't. I have no idea what columns it's indexed on because they don't include those in their names. So now I got to go look it up, you know, and spend, you know, however much time.
I got you. Yeah, there's definitely something to be said for good naming conventions from reading the query plans and, you know, not having to look all that stuff up like you said. I concur.
I include those columns in my names if I can, so that right away you can kind of get a very good picture of what the index executions are, how they're being used.
Yeah, my only pet peeve about the query plans is they tend to truncate the index names.
After a while, yeah.
So you got to hover over them and then look at the little tooltip and stuff.
Yeah.
You know. Any other questions or comments? Well, thanks everybody. Very good. Appreciate it.